single phase full wave rectifier. Full wave rectifier with center tap transformer. We have seen in the previous video what are the main parameters of a rectifier circuit. Now, let us discuss a real rectifier circuit. We are going to start with a single phase rectifier, and single phase rectifier can be obtained by different configurations. The first configuration that we are going to discuss is the center tapped transformer. Center tapped transformer is a transformer like this with a primary, but we have two secondaries, secondary 1 and secondary 2, and from these two secondary are connected to each other, and from their center we have another terminal. So center tap transformer is actually have a single input, but we have two outputs here. In this case, if the primary here is positive and negative, the first secondary, this is the positive and negative of the first secondary, while this is the positive and negative of the second secondary. Alright? If we are going to connect the first secondary with diode D1 and the second secondary from the negative terminal of the second secondary with diode D2, and we are going to connect both of them in one node and connect it to the load resistance R, and we are going to connect the load resistance to the center tap. Now let us discuss what is the mechanism of this full wave rectifier. Assuming that the voltage of the secondary is represented as a sinusoidal wave like this, which have a peak value V maximum, Vm, and multiplied by sinusoidal function sine omega t, where omega here is 2 pi over t, and t is the period of the cycle, and we are going to call 1 over t as the frequency of this signal. So omega is actually 2 pi f, and the value of omega t, if we are talking about a complete period of time t, so omega multiplied by t, it would be 2 pi over capital T multiplied by t. When the complete period, it would be from 0 to 2 pi. So the half period is from 0 to pi, and the complete period is from 0 to 2 pi. Right? So we are going to assume that the input of V source A or V secondary, for both of them, secondary 1, secondary 2, is Vm sine omega t. Okay? Now, how this rectifier works? If we are going in the first half cycle, in the first half cycle, the upper part of the secondary, this would be positive because this is positive, and this would be negative. So the first diode D1 will be forward biased because positive here is connected to B. So the current will flow from diode 1 to the resistance to complete the circuit. On the other hand, when this is positive, this means that this would be positive, or in other words, this terminal would be negative. So this terminal, which is connected to the B or the anode of this diode, would be negative. This means that this diode is reverse biased. In this case, this diode is off, so there is no current passing through this diode. So at the first half cycle, the current will pass in this way, from this direction to this direction to rotate to the resistance here. Now, in the negative half cycle or in the negative half cycle, this would be negative and this would be positive. This would be negative and this would be positive. The reverse. When this would be negative, diode 1 will be off. When this would be positive, diode 2 would be on. So now this would be positive. The current passing through the diode go to this node and pass to the resistance. So either in the first half cycle or in the second half cycle, the current in the resistor always going from this node to this node. Or in other words, this node is always positive and this node is always negative. This means that the original signal, which was AC, having positive and negative, has been converted to DC with direct current, where this is always positive and this is always negative. Let us see how. That actually the output voltage at the resistance. The output voltage at the resistance at the first half cycle, this would be positive like this. At the negative half cycle, this would be also positive like this. This means that the output at the resistance is always positive or is always direct current. The current is going in one direction always or direct. Alright? Okay. On the other hand, let us look at the diode at its reverse condition. Assume that we are in the first half. At the first half, this is V maximum or Vm passing through the diode and going to the resistance. So the voltage here, the maximum voltage here is positive Vm. Okay? On the other hand, this is positive Vm. So this is negative and this is positive Vm. So in this case, this is positive and this is positive Vm. So at the diode V diode 2, the total voltage drop, it would be the voltage drop due to the voltage at the lower part of the secondary plus the voltage at the higher part of the secondary. So both of them is going to be reversed at diode 2. This means that the peak reverse voltage at diode 2 it would be minus 2 Vm. Not only 1 Vm, 2 Vm. This is V diode 2. However, V diode 1, when it is forward, it has a voltage drop equal 0 because it is forward, assuming that ideal IV characteristic. Alright? So, in the first half cycle, the voltage at V diode 2 would be sinusoidal in negative direction with a peak not Vm but 2 Vm. So, it would have minus 2 Vm. On the other hand, when in the other cycle or in the other half cycle, in the other half cycle, this would be negative and this would be positive. This would be negative and this would be positive. So diode 1 will be off and diode 2 will be turned on. The voltage drop at diode 1 would be the voltage drop due to the upper half of the secondary plus the voltage drop due to the lower half of the secondary. So in the second half of the sinusoidal, the peak voltage at diode 1 it would be minus 2Vm. However, the voltage at diode 2, because diode 2 is forward in this case, the voltage drop would be 0. What is the problem? The problem is actually that I have a big reverse voltage at diode 2 in the first half cycle minus 2Vm, and a big reverse voltage in diode 1 in the second half cycle minus 2Vm. If this reverse voltage is greater than the breakdown voltage, the diode will be breakdown. So I wish to design a rectifier circuit which will have a reverse voltage less than this value to avoid the breakdown voltage. This is what we are going to see in the full wave rectifier based on the bridge. In the bridge, we are going to use 4 diodes instead of 2 diodes like here. Here we are using only 2 diodes. In the bridge, we are going to use 4 diodes. But the reverse voltage in the bridge would be, instead of minus 2V maximum, it would be only minus V maximum. This means that I can use the diode for high voltage without to be afraid to make breakdown. Okay? Alright. Now, let us calculate the basic parameters of the rectifiers which we have mentioned in the previous video. The first value is, what is the equivalent DC value? We have said that the equivalent DC value is, or the average value, is that if the voltage as a function of time at the load after rectification looks like this function, this means that by taking the integration of this function over the time period of this function, we can obtain the average value or the DC value. So the DC voltage or the equivalent DC voltage is effectively the integration of this cycle over its period. So actually this is half the cycle. So instead, this is a complete cycle. From 0 to 2 pi is a complete cycle. We don't need to calculate it over the complete cycle because actually the half cycle is repeated. So we are going to calculate it over only half cycle. So this is actually the period of this is T over 2. So we can say that the DC is 2 over T multiplied by the integration from 0 to T over 2 Vm, the maximum value, sine omega t dt. This actually, I'm taking the shape of this signal and integrating it over its period, and this period is only T2, T over 2, and divide it by this period 2 over T. Okay? Just to remind you, if we are talking about the integration of sine omega t dt, and we can replace omega by 2 pi over capital T, which is the time period dt. So the integration of sine is actually minus cosine omega t, and we are taking the factor multiplied by t divided, so it would be t over 2 pi. So the integration of sine omega t dt is actually minus capital T over 2 pi cosine omega t. If we are going to take the limits from 0 to T over 2, so this would be minus T over 2 pi cosine omega which is 2 pi over t multiplied by the upper limit t over 2. So this is actually cosine pi. Cosine pi is minus 1 minus cosine the lower term or the lower limit. The lower limit is 0, so cosine 0. Cosine 0 is 1. So this is minus 1 is minus 2. And we already have minus. So minus minus would be plus. 2 over 2 it would be t over pi. So the integration of sine omega t dt from 0 to t over 2 is simply 2 over pi. I'm not going to repeat these details. I'm just saying it once, and after a while you should be familiar with these integrations. Okay? Alright, so I'm going to replace Vm sine omega t dt from 0 to t over 2 by Vm multiplied by t over pi, and t can be eliminated with t, so it would be 2 Vm over pi. 2 over pi can be calculated as 0.6366 multiplied by Vm, or the maximum value. So this is the DC value or the DC voltage from this rectified signal. Okay. All right.